Higher Physics Notes, Unit 1, Section 7, The Expanding Universe. And this is Part 1, the Doppler Effect. Well, let's consider a typical example of the Doppler effect, which would be, let's say, a fire engine, as you can see in the diagram. And the fire engine is moving to the right with a velocity, which we'll call Vs for source velocity. That's the velocity of the source of the waves, in this case a sound wave. So we're imagining then that the siren of the fire engine is emitting a note. And under normal circumstances, that note would have a frequency which we'll call Fs for the source frequency. But because the source of the waves, the sound waves itself, is moving, that actually changes the frequency ahead of the fire engine and behind it, as the diagram shows. So for example, let's imagine the fire engine's going along the road and we've got two observers. One in front of the fire engine, we'll call him A, and one behind the fire engine, we'll call him B. Now, because the source itself is moving, that's the fire engine, what happens is the sound waves coming out of the siren get sort of squashed or bunched up ahead of the fire engine. And that means that their wavelength goes down, and therefore their frequency goes up, because V is F lambda, and the velocity, of course, of these waves in themselves is the speed of sound in air. So the consequence of that is that observer A hears this higher frequency. So he hears a higher pitch. So the fire engine siren would be observed by observer A, whom the fire engine is approaching. He would observe a higher frequency. We'll call that F naught at the moment, the observed frequency. And we'll deal with the equation for calculating the observed frequency in a minute. Now, simultaneously, observer B, who is standing behind the fire engine, he sees the source moving away from him. Now that has the effect of stretching the wavelength out and making it bigger. Now a bigger wavelength, of course, means a smaller frequency. Now frequency, of course, in a wave which is sound means pitch. So he's going to hear a reduced pitch, or a lower frequency sound, than he would have had the fire engine been stationary. We see that the fire engine is receding from him, it's moving away from him. That's all receding means. So to sum up, the observer whom the fire engine is approaching hears a slightly higher frequency than the rest frequency, and the observer behind the fire engine hears a slightly lower frequency than the rest frequency. And I'm sure you've all observed this as cars pass you in the street. As they're approaching you, you hear a slightly higher engine frequency, and as they recede and move away from you, you hear that dip in frequency as it recedes, lower frequency. So Doppler developed equations for working out the observed frequency, and if we deal with the source approaching the observer first, here is the equation. So first of all, we've got F naught. That is the observed frequency. So the O there is for observed, and that's in hertz. So that's what the observer actually hears. F naught is basically the source frequency. That's the frequency of the sound when the fire engine is at rest. You could think of it as the rest frequency in hertz. And that's multiplied by this modifier term in the brackets. Now, if we look at the modifier term for the approaching sound source, on the top line we have the velocity of the sound wave itself, the 340 meters per second for sound in air, and we're dividing that by the velocity of the sound minus the velocity of the source. That's the source of the sound waves. Now in this case that's the fire engine, so that's the fire engine speed Vs for source. So in each case the S stands for source and the O is for observer. So we end up then with F naught equals Fs into V over V minus Vs. And that is the Doppler equation for a wave source approaching the observer. Notice the minus sign in the denominator. Now we have a similar equation, similar but slightly different, for the receding situation. Remember, the receding frequency is perceived to be a little bit lower. Well, you can see why in the approaching equation, the one we've just done, that the observed frequency is a little bit greater than the source frequency, because if you look at that fraction, you've got V on the top, and then you're dividing it by V, take away something. So the denominator, the downstairs of the fraction, is going to be a little bit less than V. So you're dividing a number a little bit less than V into V itself. So you get a number a little bit bigger than V, and when you multiply that, a little bit bigger than 1, and when you multiply that into Fs, you obviously increase it a little bit. So F naught will be bigger than Fs. Now the receding version, well, it's got a very similar shape, but as you can see, the big difference is that on the denominator of the fraction you have a plus sign. So what does that do to the bracketed term? Well, it means V is being divided by a number which is a little bit bigger than V, so the bracketed term now becomes slightly less than 1, and when you multiply a number less than 1 onto the source frequency Fs, your observed frequency is a little bit less than Fs, and that's what we're expecting. Now in the equation list, the SQA quote both of these equations together like this. That's the combined equation, and you need to know that when the source of sound or other waves is approaching, you use the negative sign on the bottom of the fraction, and when it's receding, you use the plus sign. So always do a double check on your answer. You're always expecting an approaching sound source to have a slightly higher frequency than the rest frequency, and when it's receding, to have a slightly lower frequency. Okay, let's do an example then. So, a car is travelling at 5 meters per second towards an observer who is stationary. The car horn is sounded with a frequency of 1200 Hertz. Find the observed frequency when A, the car is approaching the observer, and then B, once it's past him and is then receding from the observer. Well, let's do part A first. So we list our variables. The speed of the source, that's the car, in this case, is 5 meters per second. The frequency of the source, the rest frequency if you like, is 1200 Hertz. The velocity of the wave itself, V, in this case is a sound wave in air, so that's 340 meters per second. And the observed frequency on approach is F naught, which is the unknown in this case. So we state our equation. F naught equals Fs times V over V minus Vs in brackets. We put in our numbers. The rest frequency or source frequency is 1200 times speed of sound is 340, so it's 340 divided by 340 minus 5. And that gives us an observed frequency on approach of 1218 Hertz. That's the approaching frequency. And as expected, it's slightly bigger than the rest frequency, the source frequency of 1200. In part B, we can use exactly the same data in part B. The only difference is that the sound source is now receding from us, so we have to use the other version of the equation. So same data, all of that data up there is still being used, but here's my new equation. Notice it's the plus sign on the bottom for receding. Put in my numbers, 1200 times 340 over 340 plus 5, and that gives me a slightly lower observed frequency of 1183 Hertz. That's the receding frequency, a little bit less than the 1200 Hertz rest frequency as expected. After you do these calculations, always just do a double check. Is my approaching frequency a little bit less than my rest frequency or source frequency for the sound or whatever wave it is? And is my receding frequency a little bit less? So the approaching frequency should be a little bit more, the receding frequency a little bit less. And that brings us to the end of the Doppler